In order to guarantee full understanding of this course, you should have completed previous universal molding modules. MU1 Introduction, MU2 Fundamentals, MU3 Molding with Graphs, MU4 Material Morphology, MU5 Press Calculations, MU6 Injection Unit Calculations, MU7 Cooling Calculations, MU8 Rheology, MU9 Injection Speed, MU10 Fill Balance, MU11 Pack Stage Calculations. Universal molding is a discipline that promotes a structure of organized events. Once again, remember that before performing a universal molding laboratory, you have to do molding from the desk. All auxiliary equipment should be properly installed and correctly operating. Temperatures, water temperature, injection barrel temperature profile, and its corresponding melt temperatures, heat zones if the mold has hot runners, etc., should already be reached. Barrel adjustments, recovery and transfer positions, decompression, recovery speed, etc., should have been programmed. The proper nozzle tip should have been installed. The required closing force should have been set. The platen openings, their movement, speeds, and mold protection should have been carefully and precisely adjusted. Extended cooling time should have been set. Remember that cooling time is set higher than required in order not to interfere in the determination of the other previously adjusted parameters. Cooling time will be optimized at the end. The ideal injection speed should have been determined, adjusted, and should be filling over 95% of the required fill for the mold. The injection pressure limit should have been determined and adjusted. The pack stage should stay off. Pack pressure and time should have been determined and adjusted. The leftover cooling time should have been adjusted. Important: the equipment should only be operated and/or adjusted by qualified personnel who have read the operational manuals of the equipment and have mastered the equipment's functionality. In this course, we will discuss Review, Cooling and Recovery, Understanding your product, Cooling time, Optimization using the mold temperature, Other parameters that affect cooling. Review, Cooling and Recovery. Cooling. In this stage, we remove heat from the parts until we obtain parts that can be demolded with thermally accepted dimensions. The idea is to manipulate the removal of heat from the melt in order to control the thermal dimensions. Remember that a rapid cooling rate results in thicker walls and a slow cooling rate results in thinner walls. Familiarize yourself with your machine's controls, since some controls include pack time inside of the cooling time. Be careful with this stage. Extensive cooling times can result in costly processes. The idea is to manipulate both parameters, temperature and cooling time, in order to obtain the optimal dimensions.
Can the mold's temperature affect the pack time?
Yes, it can, since any change in the way heat is removed from the melt will have an effect on the time it takes for the gate to freeze.
How do we control the temperature of the mold?
We can change the temperature of the water that cools the mold cavities and sometimes even modify its flow. It is important to understand that the temperature of the water that enters the mold and the mold's metal temperature are distinct. Remember, thermal dimensions are a function of shrinkage and not a function of the amount of packed mass. Cold molds and extended cooling times will result in thicker walls. Hot molds and short cooling times will result in thinner walls. The speed with which heat is removed can affect other mechanical properties, such as rigidity, translucency, crystallinity, etc. Recovery. The main objective of recovery, also called plastification or plasticizing, is to consistently produce a homogeneous melt. During recovery, the check ring moves to the front, permitting melt to pass in front of the screw. Remember that recovery happens at the same time as the cooling stage. Under normal conditions, recovery ends before cooling does. If cooling finishes first, the control will not allow the mold to open. This condition will extend the cooling time and consequently will also affect the thermal dimensions. During recovery, the mold is closed and full of material. It is this material that keeps the melt inside the injection unit. After recovery, the melt is compressed. If the mold opens and demolds the finished parts, the melt could drool inside the open mold. This is why there must be decompression after recovery. There can also be decompression before recovery.
How can there be decompression before recovery if the injection unit is practically empty?
Though not so common, in some molds this movement helps with sprue removal. Remember, if the mold opens during recovery, and neither the injector nor the mold includes some valve system for closing, the plastic will drool inside the mold. As a general rule, recovery should end about 1 second before cooling does. It's important to know that the injection unit uses 2 sources of heat in order to melt the plastic: heater bands and friction. Though the operator programs the heat zones of the barrel, the melt temperature is the most significant factor. Understanding your product. Optimizing the cooling stage will depend upon the type of product. Before making any decisions, ask yourself the following. 1. Which effects need to be optimized in the cooling stage? 2. Is shrinkage significant in the product? 3. What factors or parameters must be evaluated that could contribute to the thermal effect or effects?
What other parameter could affect the optimization of the thermal effects of the molded product?
It was previously mentioned that there are basically 2 parameters that should be optimized: cooling time and cooling temperature. However, there are other parameters that could affect heat removal and, consequently, the thermal dimensions and the properties of the molded product. An example of this is melt temperature. Hot melt would require more heat removal during cooling than a cooler melt would.
Is the melt temperature of a thermoplastic melt a set value?
Not for each molding application. Molds that are difficult to fill could require an increase in melt temperature. Filling cavities with thin walls could require more energy than cavities with thick walls, even though they are filled with the same thermoplastic. Remember that an increase in melt temperature reduces viscosity. Understand your product before deciding which parameters could affect your product in the cooling stage. The optimal thermal effect could be a function of 1 factor, mold temperature, 2 factors, mold temperature and cooling time, or 3 factors, mold temperature, cooling time, and melt temperature. Cooling time. We know that long operational cycles can be costly. Consequently, the cooling time should be reduced as much as possible. To reduce the cooling time, you should carefully lower it until reaching the minimum amount of time needed to demold parts that are visually acceptable. You must be extremely careful during this process. Parts trapped inside the mold could result in costly damage. In molds with cold runners, the runners could be used as a reference at the moment of demolding. The runner is usually thicker than the molded parts, and how it demolds could be used as a reference for the reduction of the cooling time.
Once we reduce the cooling time value, have we finished with its determination?
Not necessarily. You will probably have to modify it to guarantee some dimension or property of the molded parts, and will have to repeat the experiment with additional cooling parameters. Optimization using the mold temperature. This procedure is the simplest and probably where everyone should begin. Step 1. Determine the minimum cooling time. Carefully and without reaching the recovery time, reduce the cooling time until you reach the least amount of time required to demold visually acceptable parts.
What happens if the recovery time is reached and the cooling time of the mold can still be lowered?
If the process permits, reduce the recovery time by increasing recovery speed, guaranteeing that the entered cooling time isn't affected by the recovery time. Once again, avoid closing the mold with parts inside. This could cause expensive damage. Step 2. Organize and create a table for your experiment. Select a range for your experiment, for example 70 plus or minus 4 degrees Fahrenheit. This range could be obtained from the material spec sheets, from the mold manufacturer, or from a trusted molder who has molded with this material or a similar product. Decide how many times each experiment will be repeated. Don't overload the experiment. 3 to 5 repetitions should be sufficient. Include the following in the table: the 2 temperature levels, the number of repetitions, 3 for each temperature, spaces for the random order in which the experiments will be performed, spaces for the molded parts dimensions or attributes that will be evaluated, and spaces for the averages of the measurements.
How can you measure an attribute or a visual effect?
Though the measurement will be subjective, a judgment scale can be established. For example, select a person that understands the effect being measured and ask him or her to evaluate that effect using a scale from 1 to 4, where 1. No defect is detected. 2. The defect is insignificant. 3. The defect is notable. 4. The defect is unacceptable.
Why does the laboratory need to be randomized?
Though it may seem strange, randomizing the temperature changes in the experiments gives results that are closer to reality than when using ordered changes in temperature. Randomized changes lessen the possibility of error due to human convenience. Step 3. Write a protocol of how to perform the laboratory. Reduce any objectivity by writing specific procedures that everyone has to follow. Example of a simple protocol. 1. Verify that the cooling water source, chiller or cooling tower, that supplies the mold's water temperature control is at least 5 degrees centigrade, or 9 degrees Fahrenheit, colder than the lowest temperature that you expect to program. 2. Determine the limits of the water temperature that correspond to the limits of the mold temperature. Remember that the water temperature of the mold is normally different from the temperature of the metal of the cavities. 3. Between experiments, stop the machine until reaching the adjusted temperature. 4. Once the temperature is reached and the machine is operating normally, wait 10 cycles to take the sample. 5. The measurement should be taken by the same person in the metrology laboratory with a calibrated instrument. 6. The measurements will be performed in order. For example, 2 hours after being demolded. Step 4. Perform the laboratory and enter the results in the table. Follow the protocol procedures that were approved for this laboratory and perform the experiments, complete the table, and calculate the corresponding averages. Step 5. Evaluate the results. Evaluate the results and select a temperature range that guarantees a measurement of the parts or the effect that you are looking for. Step 6. Corroborate the ranges of the selected temperatures. Inside the limits of the selected temperatures, take multiple samples at distinct periods and verify that those results comply with the prediction of the effect that is being studied. Example. This exercise was performed by students at the University of Puerto Rico in Mayagüez. The material is low-density polyethylene, and the product is Acme brand. The laboratory was performed in order to measure the effect of the mold's temperature on shrinkage. The students decided on the following critical measurement: 2.694 plus or minus 0.03 of an inch. The material spec sheets applied by the resin manufacturer listed a range of 70 degrees Fahrenheit to 90 degrees Fahrenheit for the mold temperature. Experiment protocol: 2 temperature levels of 70 degrees Fahrenheit and 90 degrees Fahrenheit. 3 repetitions for each temperature level. Each experiment was randomized. The cooling time was set to 18 seconds. The machine was stopped between experiments until it reached the adjusted temperature. Once it began operating, the sample was taken after the 10th cycle. Measurements were taken in order 2 hours after demolding. The same person took all the selected measurements. The operator verified during the experiment that the mold never closed with parts trapped inside the cavities. Results of the experiment. For a mold temperature of 70 degrees Fahrenheit, the average length in cavity 1 was 2.703 and in cavity 2, 2.701. For a mold temperature of 90 degrees Fahrenheit, the average length was 2.686 in cavity 1 and 2.685 in cavity 2. To understand the effect, graphs of temperature versus dimension are created, one for each cavity. The graph of length versus temperature reveals a clear effect of the temperature on the length of the parts. Drawing a line at the average length of 2.694 inches, we can predict that cavity 2 should be around 78 degrees Fahrenheit and cavity 1 should be around 80 degrees Fahrenheit in order to guarantee the average length. With a prediction equation for each cavity, we can simplify the selection of an acceptable temperature range. In this example, the equations are simple since it is the equation for a line. Normally 2 points are sufficient, but if you suspect that the results are not lineal, you can use intermediate points. The corresponding lineal equations will be the following. Cavity length 1 equals 2.763 minus 9/10,000ths times T sub m. Cavity length 2 equals 2.7592 minus 8/10,000ths times T sub m. These equations come from the equation for a line y equals y naught plus mx, in which y is the length, x the temperature, y naught the intercept in the coordinate of the length, and m the slope. Solving the equations for temperature, we obtain the following. T sub m equals 2.7630 minus the first cavity length, all divided by 0.0009. T sub m equals 2.7592 minus the second cavity length, all divided by 0.0008. Substituting the temperature limits, 2.694 plus or minus 0.003, of 2.697 inches and 2.691 inches in both equations, we obtain the following. For temperature cavity 1, the upper dimension will be 73 degrees Fahrenheit, the lower dimension will be 80 degrees Fahrenheit. Temperature cavity 2, the upper dimension will be 78 degrees Fahrenheit, and the lower dimension will be 85 degrees Fahrenheit. We evaluate the results. If the temperature of the mold is adjusted to 73 degrees Fahrenheit, cavity 2 will be outside of the range, since its minimum is 78 degrees Fahrenheit. If the temperature is adjusted to 85 degrees Fahrenheit, cavity 1 will be outside the range, since its maximum is 80 degrees Fahrenheit. The operational range will then be between 78 degrees Fahrenheit and 80 degrees Fahrenheit. Other parameters that affect cooling. Though the cooling stage's control parameters are cooling time and mold temperature, we must recognize that melt temperature contributes as well. Imagine a product that, after performing the previous mold temperature exercise, needs better thermal dimensional control. A decision was made to optimize these thermal dimensions by evaluating the contribution of three factors. T sub m equals temperature of the mold, T equals cooling time, and T sub f equals the temperature of the melt. The critical dimensions could be represented by the following lineal equation, in which average measurement equals D sub C, effect of the mold temperature equals B naught times T sub m, effect of the cooling time equals B sub 1 times T, effect of the melt temperature equals B sub 2 times T sub f, and the combined effects equal B sub 3 times T sub m times T through B sub 6, T sub m, T sub f, T. The symbols B naught to B sub 6 are constants.
Why assume that the behavior is lineal?
Excellent question. If the universal molding laboratory is performed in the recommended order, including optimizing the mold temperature and selecting reasonable experimental ranges for each factor, we can assume a lineal effect will be more than sufficient.
What would be reasonable experimental ranges for each factor?
If the experimental ranges are very large, for example plus or minus 10 degrees Fahrenheit for the melt temperature, you can be sure that the results will not be lineal and will require a more complex equation. An exercise of three parameters or factors consumes time and resources. Be careful with your design or you could end up with inconclusive results. Let's look at another example in which we suspect that the pack pressure has a significant effect on the dimensions of the product. In this exercise, we presume that the critical dimensions, besides being a thermal function, are a function of the quantity of material and should consider the following three factors. T sub m equals mold temperature, T sub f equals melt temperature, and P equals pack pressure, in which average measurement equals D sub C, effect of the mold temperature equals B naught times T sub m, effect of the pack pressure equals B sub 1 times P, effect of the melt temperature equals B sub 2 times T sub f, and the combined effects are B sub 3 T sub m P through B sub 6 T sub m T sub f P.
What is a combined effect?
A combined effect is when two or more factors or parameters join together to influence the effect that is being evaluated. A hypothetical example. Two employees work separately, but at the same job. Their job is packing molded products into boxes, and each employee packs 50 boxes every day. One day they decide to work as a team, with one employee assembling the boxes and filling them with the product, and the other one closing and stacking each box. At the end of the day, they pack 120 boxes. With their combined effort, they pack 20 more boxes each day. This also happens when two parameters combine and create an effect on the molded product.
How do you perform an experiment like this?
Start by organizing the experiment. First, establish an objective and the effect or effects that will be measured. Second, identify which factors or parameters you believe have some effect and how they are related with the effect you are going to examine. Selecting these factors is probably the most delicate part of this process. Include only those factors that have a high probability of influencing the effect that you are evaluating.
Wouldn't it be better to perform these experiments with the largest number of factors?
Don't complicate your laboratories. Most can be performed with just one factor, mold temperature. Then, if you are unable to optimize the effect, consider a second factor, and if necessary, consider up to a maximum of 3 factors. The cost and time to perform the experiment increases considerably with an increase in the number of factors. What's worse, the results are not necessarily better when increasing their number. Third, select the limits or ranges for each factor. Here you need to be very selective. Too big a range could create nonlineal results, create inconclusive results, or could complicate the experiment. Too small a range could reveal no contribution to the effect, though some contribution may exist. For example, a range of plus or minus 4 degrees Celsius for mold temperature could work, but may be too large a range for the melt temperature. Fourth, create a table for your results. Create spaces for the variables of the effects and their combinations, the number of repetitions, and the numbers of the experiments. Fifth, write a protocol on how the laboratory will be performed. Sixth, perform the laboratory and take the samples by following the written protocol. Seventh, evaluate the data and obtain results. If the laboratory uses 2 factors, example cooling time and mold temperature, with a mold that contains only a few cavities, 4 or less, the data analysis could be performed in Excel. However, with more than 2 variables and more than 4 cavities, you will need to use a statistical program. The results should reveal the significant and non-significant factors and the significant and non-significant interactions. For example, in an experiment with 3 factors, mold temperature T sub m, cooling time T, and melt temperature T sub f, we use the following formula. It was discovered that 1. Cooling time T is not significant, and 2. The combined effects of B sub 3 T sub m T, B sub 5 T T sub f, and B sub 6 T sub m T sub f T are also insignificant. The equation can be reduced to the following. In which the critical dimension is affected by the effect of the mold temperature, the effect of the melt temperature, and the combined effect of the mold temperature and the melt temperature.
Let's review.
Summary. Begin the optimization of the cooling stage by finding the minimum cooling time that produces parts that can be demolded and that are visually acceptable. The first laboratory should only be performed with the temperature of the mold. Consider a second factor only when the cooling stage cannot be optimized with the temperature of the mold. When the effect is an attribute, for example a visual or physical defect, select one person who knows how to evaluate the effect and establish some numerical evaluation system that represents the criteria for acceptance. In order to reduce the possibility of objectivity on the part of those performing the laboratory, create a written, step-by-step protocol that must be followed. If the laboratory is for two factors, example cooling time and mold temperature, with a mold that has only a few cavities, 4 or less, data analysis can be created in Excel. With more than two factors and more than 4 cavities, you should use a statistical program.
You have completed this lesson.